How's it going, guys? So in this recording we're going to be going over one-sided limits. Now before we get to one-sided limits though, I first want to review the concept of piecewise functions. Now piecewise functions are just a function that is defined differently on different parts of its domain. Now the reason I want to review them is because I know that it can be a topic that maybe you have not seen, or maybe you saw a while ago and maybe it was a little bit confusing. So piecewise functions will be appearing on calculus here, and I just want to make sure that we all know what they are and we all know how to graph them and interpret them. Now I have posted here an example of a piecewise function. Now the way that piecewise functions work, as you can see here, is it seems to be that you have two, or you might even have more functions at once. Now the f of x is just telling you it is the name of the function. Then you have the bracket here. Now this bracket is indicating a piecewise function, and then you have what I like to call the pieces of the piecewise function. So you have here that f of x is 2x plus 3 if x is less than or equal to 0, and negative x minus 1 if x is greater than 0. So let me label them here as piece 1 and piece 2. Okay, so the if conditions here are very important, because what you're saying here is that the function is going to take the form of either of the pieces depending on what your input is. So for example, if I were to put in an input that is less than or equals to 0, then I need to select piece 1. But if I were to select an input, an x value that is greater than 0, then I would have to select piece 2. So these ones here are very important. This is the conditions for piece 1, and these are the conditions here for piece 2. I just put here piece 2. Now let me just give you an example here before we graph them. Let's say that we were given this function and I wanted you to find out the following. What is the function evaluated at, let's say, a -1, and what is the function evaluated at, let's say, a 5? Okay, now we've already taken a look at how to evaluate functions, and yeah, I know you guys have done this quite a bit in the past. So remember, they're just telling us that right now, okay, the input is -1, so we're going to plug in the -1 into the function. But again, this is where the conditions come into play. Is the input less than or equal to 0 or greater than 0? Well, the -1 is less than or equal to 0, so that means that you're going to go to piece 1. Okay, so if I go to piece 1 said that it was 2 times the input plus 3, so 2 times the input plus 3. And this is going to give us here, let's see, 2 times -1 is -2, plus 3 is a 1. Okay. Now notice I did not plug in the -1 into the second piece because the x was not greater than 0. It's all about noticing what are your inputs that you're putting in and what are the conditions for the given pieces. So if I wanted to find out, okay, what is the function evaluated at 5? Well, now the 5, the input here, is this less than or greater than 0? Well, the 5 is greater than 0, so that means that now you're going to be selecting piece 2. Okay, so we're going to have, what was piece 2 asking us to do? It was a -1 times the input plus or -1. Okay, and that's going to give us here -5 minus 1, that's a -6. So there you go. Notice again, one input, one output. You don't plug in the input into both pieces, guys. Just take a look at what are the conditions, so then you can determine which piece you're going to be selecting. Okay, and piecewise functions are very important. They do have a lot of uses. Just to make sure that we all know what they are and how to interpret them. Okay, now let's take a look at the piecewise function here, and let's graph it and see how the graph looks like. So again, we have the function f of x is 2x plus 3 if x is less than or equal to 0, or f of x is -x minus 1 if x is greater than 0. Now there's different ways of graphing them. The one that I'm just going to be choosing right now is the more traditional way of basically making a table and graphing the points. So we just go to the tried and true method of point plotting. So I'm going to put piece 1 here, and I'm going to create a table. Okay, so we're going to have the x and the y being the 2x plus 3. Now remember, for piece 1, the condition was that the x values, the inputs, are less than or equal to 0. Okay, so I'm going to select values of x that are less than 0. Let's go with a -3. Actually, let's just go with -2, -1, and 0. I think 3 points would be enough. Okay, now we start figuring out, okay, what are the y values that we're getting? So let me just copy things here. Actually, let's put the x's in orange. Or actually, let's do plum instead. There we go. Those are my inputs. Okay, so what y values we're going to be getting? Let's see, 2 times, 2 times, 2 times, and plus 3, plus 3, plus 3. So let's see, -2, -1, 0. All right, so the values that we will be getting are the following. 2 times -2 is -4, plus 3 is -1. Then 2 times -1 is -2, plus 3, that's a 1. 2 times 0, 0 plus 3 is 3, okay? And there we have these 3 points. Now, one thing that I want to mention here is, notice that for the inputs, I selected the 0. And I would say that the 0 is special because it just happens to be the endpoint of the pieces here, or the interval of the pieces. It's like the endpoint of the domain. Now, in this case, because x is allowed in the domain for piece 1, I'm going to make a note here and say that this point is a closed circle. Because again, the inputs, the x's, are less than or equals to 0. And the reason I'm bringing it up here is because take a look at the second piece. So when we make a table for piece 2, let me just put here piece 2. Now our x values, our inputs, have to be less than 0. So 0 is technically not allowed in that piece. But when you guys make a table, I do want you to include the 0. So let me just make a table here with the x's. And piece 2 was -x plus 1. Oops, -1. There we go. Okay, so I'm going to select some x values here. Let me just copy the y's. Well, actually, let's select some x values. And again, as I was saying here, I'll include the 0. Then values of x that are greater than 0 are 1 and 2. So we're going to have here our y values given by, let me put the x's in orange here. So 0, 1, 2. So -0 minus 1, that's a -1. -1 minus 1, that's a -2. And -2 minus 1, that's a -3. Okay. Now, why did I mention that we needed to include the 0 even though the x has to be greater than 0? Well, the reason for that is illustrated more clearly here in the graph. Let's say that I did not include the 0, but I included the 1 and the 2. So when x is 1, the y value is -2. When x is 2, the y value is -3. Okay. And all the other points, well, you can see here that we do have 2 points, and that's all we need to make a line. So there we go. Here is piece 2. But notice here that I'm saying that all the x values have to be greater than 0. And at first glance, it seems like that's what we have. But what about, let's say, a 0.5 here? Is 0.5 greater than 0? Yeah. What about a 0.1? 0.1 is greater than 0. So you see there's a lot of values that I'm not including here. Now we avoid that issue by saying that we are going to be including the 0. However, it's going to have an open circle. So if we have an open circle here, we're saying that, okay, exactly at 0, you don't have any values for the function because it's not in the domain, but a 0.1 or a 0.005 is still included. So it still has to be part of our line. And that's what we do here with the open circle. We're saying that that specific point is not there, but anything to the right of it is there. So make sure that you include the endpoints, guys, of the pieces. Now, if it's included, it's a closed circle, but if it's not included, if it's only a greater than or less than, then this one here is an open circle. Okay, so we graph piece 2. Now let's take a look at piece 1. Well, piece 1 told us that when x was -2, then the y value was -1. So let's see, when x was -2, then -1. When x was -1, we got 1. There we go. And when x was 0, we got 3. So 1, 2, 3. There we go. I think I made a mistake here. Doesn't seem. 3, 1, -1. So, oh yeah. I missed the mark. 0, 3. There we go. Now, again, the 0 was a closed circle, so I'll just emphasize it here. Closed circle, there we go. And we just now finish the line here. And again, notice that I'm including arrows in both of the pieces because there was no other restriction in the domain. We're just saying that we're including all the x values that are less than 0 for the first piece. That's why we draw an arrow, still heading towards the left. And on the second piece, x was greater than 0, so yeah, the x values can still keep on increasing without really stopping. Okay, so that's how we graph the piecewise function. And as you saw, it was pretty much just graphing each piece individually, but again, taking care of or paying special attention to the endpoints here, making sure that we know whether it's going to be an open or closed circle. Okay? Now, with that said, we are ready to begin with the one-sided limits. So let's take a look at the definition here. As x approaches a, the limit of f of x is L if the limit from the left exists and the limit from the right exists, and importantly, both limits are L. Mathematically, what this means here is the limit of f of x as x approaches a, now this subtractions here just means from the left, equals to the limit of f of x as x approaches a. This addition symbol here means from the right. So if the limit from the left equals to the limit from the right, then the limit as x approaches a for f of x is L. So again, notice that both limits have to be equal. And we saw here that the limit of f of x as x approaches a, subtraction here means from the left, meaning that you're selecting x values that are less than a. And the notation here where we have the limit as x approaches a, subtraction, that just means from the right, where the values of x are greater than a. Now, I want you guys to be careful, because what we just said was that the limits coming in from the left and the right had to be equal. Then the limit was indeed L. However, if the limit as x approaches a from the left does not match the limit as x approaches a from the right, then the limit does not exist, which we can abbreviate here with D and E. So this is going to be the first instances, guys, where we are going to be encountering examples where the limit does not exist. All the other ones that we've done before, yeah, the function seemed to be approaching a particular number coming in from both directions, but let's take a look at an example here where that's not necessarily the case. So let's take a look at example 4, where it's asking us to graph the following function and evaluate the limits if they exist. So the function here is h of x equals to the piecewise function 2x plus 2 if x is less than 1, and 2x minus 4 if x is greater than or equal to 1. All right, so we're seeing here a piecewise function, and we want to find out what is the limit of h of x as x approaches 1. Okay, now we don't know how to find limits algebraically yet, so let's actually make a graph and see if we can find the limit graphically. All right, so I'm going to go ahead and graph piece 1 here and piece 2. Okay, so making a quick table of values for piece 1. Oops, 2x plus 2. And that was if x is less than 1. Okay, so we're looking for values that are less than 1. So I'm going to put a -1, a 0, and as I mentioned before, I will be including the endpoint, but recognize that this one here is going to be open. Okay, so what are going to be the y values that we get? Well, 2x plus 2, where x is -1. I believe that's going to give us a 0 here. Now let me write it here on the right hand side. 2 times the x values, and then we add 2. There we go. The x values being -1, 0, and 1. Okay, so 2 times -1 plus 2 is 0. 2 times 0 plus 2 is 2. And 2 times 1 plus 2 is 4. Okay, so there are the points. So let's go ahead and plot them. When x was -1, we got 0. When x was 0, we got 2. And when x was 1, we got 4. But it was an open circle. And there we go. We get to see part of the graph here. Something like that. Okay, now this one here was piece 1. Let's go ahead and do piece 2. Oops, piece 1. There we go. Here is piece 2. Y equals 2, 2x minus 4. And now we're selecting values of x that are greater than or equal to 1. So let's go with 1, 2, and 3. And let's see what y values we get. Okay. So if x is 1, 2 times 1 minus 2 is -2. If x is 2, 2 times 2 is 4, minus 4 is 0. And if we put in 3, 2 times 3 is 6, minus 4 is 2. Okay. So here is the values that we're getting for piece 2. So if x was 1, we got a -2. And one thing to note or to notice is that 1 was allowed. So this one here is closed. Okay, so we put the closed circle there. Now if x is 2, the y was 0. And if x was 3, the y was 2. Okay, and now we can just continue on with the graph. Okay, so we got here a very rough sketch. Now let me just make this a little bit smaller. Okay, alrighty, so now let's actually go ahead and find the limit. So what is the limit for h of x as x approaches 1? Now, I want you guys to be very careful of this. Whenever you're encountering a piecewise function, and you're being asked a limit, normally it's not too bad unless the value that x is approaching happens to be the endpoint of the piecewise functions. Because if that's the case, we're going to have to do, oops, there we go. We're going to have to do one-sided limits. Okay, so I'm going to do the one-sided limits. I'm going to first do the left approaching from the left. Well, approaching from the left, let's see the limit as x approaches 1 from the left for h of x, and the limit as x approaches 1 from the right for h of x. Okay, so let's see. As I'm approaching 1 from the left, let's see what's happening on the graph. You're getting closer and closer to 1 coming in from the left. Well, if you notice, if you're coming in from the left, it looks like the behavior of the function is the same as piece 1. So I'll just put here piece 1. Because again, you're coming in from the left, and on the left of 1, you are using essentially piece 1, so we're going to have the limit for h of x, which is now behaving like piece 1, 2x plus 2, as x approaches 1 from the left. So what y value are you approaching? Let's see, as I'm coming in from the left, the y value that I'm getting closer and closer to seems to be the 4. Okay, so the limit is 4. Now what about the limit as you're approaching 1 from the right hand side? Well, as now I am approaching 1 from the right hand side, it looks like the function is behaving like piece 2. So I'll just put here piece 2. So we have then the limit. Oh, let me just move this a little bit further up. There we go. So we're going to have the limit as x approaches 1 from the right hand side, and the function is behaving just like piece 2. So it's a limit of 2x minus 4. Okay, so what do we get there? Well, let's see. What is the function value approaching? Well, as I'm getting closer and closer to 1, the function seems to be getting closer and closer to a -2 here. Okay, so you're approaching -2. Perfect. Now, if I were to ask you though, what is the actual limit at 1? Because what we just found was a limit at 1 coming in from the left and at 1 coming in from the right. But if you were to come into both, approaching 1 from both directions, well, these ones here, they don't match. So then what we're saying here is that the limit coming in from the left is not equal to the limit coming in from the right. So therefore, the limit does not exist. So our answer here, the limit, maybe I should have left more room, but in this case, the limit for h of x as x approaches 1 does not exist. Because again, the limit coming in from the left did not match the limit coming in from the right. Okay. Now, what about the second example, where it's asking us to find out, hey, what is the limit for h of x as x approaches 3? Well, do we need to do the one-sided limits one more? Well, take a look at it here. We're approaching 3. Was that the endpoint for any of the piecewise functions? Not really. 3 is located right over here. When x is 3, well, if you were to come in approaching 3 from the left and the right, it looks like the y value that you're approaching is still a y value of 2. This one here had no problem. We're just tracing, hey, as the x gets closer and closer to 3, what are your y values getting closer and closer to? Well, a y value of 2. So that is the limit. Okay? So these are the concept of one-sided limits. We don't have to approach the x value from both sides all the time. We can actually just split it up and approach from one particular direction at a time, from the left and the right. Okay? Alrighty, so this is it for one-sided limits. In the next video, we're going to be talking about limits involving infinity. I'll see you guys.